Welcome dear audience, students and scholars. Here I am Dr. Amjad Ali. In this video we will learn an interesting topic, that is dummy variables. In this video we will learn the definitions of the dummy variable, the uses of dummy variable trap, and how can we remove the dummy variable trap, and the use of dummy variable in regression analysis with one quantitative and one qualitative variable, and with more than two dummy variables, and how can we find the structure break in our data with the help of dummy variable. So let's discuss the definitions of dummy variable. It is a representative of indicator variable, categorical variables, qualitative variable, or dummy variable. An indicator variable is a variable that can assume either of only two values like 0 and 1, where one value represents the existence of a certain conditions and the other value indicate that condition does not hold. The category for which no dummy variable is assigned, known as base, benchmark, comparison, or control category. All the comparison is made in relation to the base category. The nature of the dummy variables. In regression analysis, the dependent variable or regressions is frequently influenced not only by ratio scale like income, output, price, cost, height, temperature, but also by variables that are essentially qualitative or nominal scale in nature, such as sex, race, color, religion, nationality, geographical region, politics, or political upheavals, and political party affiliation, like that. For example, holding all other factor constant, female workers are found to earn less than their male counterparts, or non-white workers are found to earn less than whites. This pattern may result from sex or racial discrimination, but whatever the reason, the qualitative variables such as sex and race seem to influence the regression or your independent variable, and clearly should be included among explanatory variables or the regressors. And the way we could quantify such attributes is by constructing artificial variable that takes on values like 0 and 1, or 1 or 0, and here 1 indicates the presence of attributes and 0 indicates the absence of that attribute specifically. Variables that assume such 0 and 1 value are called dummy variables. Such variables are essentially a device to classify data into mutually exclusive categories such as male or female, or white and black, and or on the basis of geographical region as well. The use of dummy variable. Dummy variables are mainly used as a proxy for those variables which cannot be measured in any particular situation for various reasons. They are some of the uses of the dummy variables here, like when we are talking about we cannot measure such variable like race, love, and such qualitative variables cannot be directly measured. So there are some uses of dummy variables in econometrics. The dummy variables are widely used as a proxy for qualitative factors such as gender, color, religion, and profession. Let's consider a demand model here. Demand model here, like QD is the function, or QD depend upon prices, income, and urban or rural population, or urban or rural areas. So here we have a price data and we have a income data in a quantitative shape, but we cannot measure urban or rural category or geographical region. So for that we have to use a dummy variable here. Let's say D. If 1 if a person belong to urban area and 0 otherwise. If we put a 1 here, then we get the demand function for the urban area, and if we want to see the demand function of the rural area, then we put a 0 here, then we get the demand function of the rural areas or rural population. Okay, dummy variable may also use as a qualitative regressor when no observation on these variables are available, or when it is difficult to collect accurate information on the variables. Like we have a different age groups can be introduced in a different in a model by using dummy variable, like age group from 20 to 30, from 30 to 40, like these type of groups can be introduced in the model. So these groups will represent the dummy variable. Okay, dummy variables are used for measuring the shift of a function over time. The shift of a function implies that the intercept change in different period while other coefficients remain changed. Dummy variables are used for measuring the change of slope over time, like we are going to consider the comparison between peacetime and wartime, the growth of a peacetime and the growth of a wartime, and the consumption of a peacetime and the consumption of a wartime. Okay, dummy variable can be used as a proxy for the dependent variable. In this case, dummy variables can take 2 or more value. When the dummy variable take only 2 values, it is a dichotomous variable. Like we are considering dummy variable if 1 if a person belongs to urban area and 0 otherwise. In this case, the dummy variable calls a linear probability model. This is also known as a linear discriminant function. The probability or log model can be used for this particular purpose. Dummy variable can be used to test the stability of the regression coefficient. The definitions of the appropriate dummy variable depends on whether we are using the analysis of a covariance test or the predictive stability test for the stability. Interaction effects can be studied with the help of dummy variable. Dummy variables are also used in piecewise linear regression model. Dummy variables can be used where some parameters across equations are equal. Dummy variables also used to deseasonalize econometrics time series, like we have here yt is equal to beta naught plus beta 1 q1 t plus beta 2 q 2t plus beta 3 q 3t plus ut. And if we want to see the effect of quarter 1, quarter 2 and quarter 3 like this, so if we want to see the impact of quarter 1, we generate a dummy like 1 for the first quarter and 0 otherwise. We put a 1 here and 0 here and here, then we get the effect of the first quarter. And if we want to see the effect of second quarter, then 1 for the second quarter and 0 otherwise, and we put a 0 here and 0 here, and then we get the effect of the second quarter. Like that we get the effect of the second quarter as well. If we put the 1 here, 0 here, 0 here, because except quarter 3 we have a 0 everywhere. So with the help of dummy variable we can find the seasonal impact of our independent and dependent variable. Dummy variable trap. If a qualitative variable has k categories, introduce only k minus 1 variable, otherwise the situation of perfect multicollinearity arises and the researcher will fall into dummy variable trap. This is also applies if we have more than one qualitative variables in the model. The number of dummy variables introduced must be one less than the categories of the variable for each qualitative variable. Like we have here yi is equal to beta naught plus beta 1 x I plus beta 2 x I plus beta 3 x 3i plus ut. Here we if we are taking the dummy variable x2i, if 1 for male and 0 otherwise, and we are taking the other category, 1 for male and 0 otherwise. In such situation, a researcher falls in dummy variable trap, and we cannot find. So if we introduce two dummy variables in this model like x2, xi and x3i, so researcher will fail to estimate the regression model. In this case, there is a perfect linear dependence among independent variable, and normally this is technically known as a multicollinearity among the variables, and the researcher who includes dummy variable like x2 and x3 falls in a dummy variable trap. To avoid dummy variable trap, there are two ways how can we escape from dummy variable trap. The first one by dropping intercept term. The second one is by deleting one category. So let's start the first method or first way to avoid dummy variable trap, and the first one is by dropping intercept term. Introduce as many dummy variables as you want, the number of categories you have for your variable, but do not introduce intercept in the model. Like in this way you cannot fall into a dummy variable trap. Like you have a model here, y is equal to beta 1 x1i plus beta 2 x2i plus beta 3 x3i, and you are including a dummy variable for x2 and x3. So see here we have not intercept. So when we have not intercept in our regression model, there is no issue to indulge ourselves in a dummy variables trap. So moreover, there is no longer perfect multicollinearity among our independent variables, and now we can find the coefficients of our regression analysis. By deleting one category, the more commonly used method for avoiding the dummy variable trap is deleting one category by introducing the intercept in the model. If you want to include the intercept in your model, but you want to avoid the dummy variable trap at the same time, then you have to remove one category of the dummy variable in your model. So let's see, we have a yt is equal to beta naught plus beta 1 xi1 plus beta 2 x2i plus beta 3 x3i plus ut. So if you want to introduce different dummy variables, so make it clear that there is no much difference who category you are going to meet or who category you are going to delete. Different values are obtained by the relationship among the coefficients are the same. If you are deleting this category or this category, your results will be, or your coefficient will be remain same. So by deleting one category, you get your result without the multicollinearity issue. Regression analysis with dummy variables. This is a more important discussion. Now we have regression analysis with dummy variables. Regression equation with one qualitative and one quantitative and one qualitative or one dummy variable. Let we have a model here, yi is equal to beta 1 plus beta 1 d plus beta 2 x plus u. Here we have a one quantitative variable and one dummy variable. So let's start the discussion here. If we want to see the salary of a male or a female, or you can say with respect to male or female. So let we have a dummy variable here, one for a male, if this is a model for the salary of a male or female. So if there is a male, then put it 1 here and 0 otherwise, and 1 here and 0 otherwise, we get the salary of a male. And for the salary of a male, the regression equation will look like that: y is equal to beta naught plus beta 1, because here we put a 1, so we get a higher constant as compared to main regression line. So we have a constant with beta naught plus beta 1. So this is our salary of a male. But if for the salary of a regression, for the female salary regression line become as, because here we suppose that 1 for male and 0 otherwise. If we put a 0 here, then the regression line for the female salary become as yi is equal to beta naught plus beta 2x plus ut. Okay, we are discussing the regression analysis with dummy variables. So here regression equation with 1 quantitative and 2 dummy variables. More important, 1 quantitative with 2 qualitative variables. Like here we have a y I is equal to beta naught plus beta 1 d1 plus beta 2 d2 plus beta 3x plus ut. So keep in mind, here we are going to find salary of a male or female, and here we have include another category, that is a white male or white female, or white or black or white we are including here. So let's introduce the first dummy variable. Like here we have a 1 for male and 0 otherwise, and the second dummy variable is 1 for white and 0 otherwise. We are finding the salary of a white male or female, or black male or female, like that. Okay, now male salary become as, here we put because here we are not giving the dummy variable, like we are only starting from the first dummy variable, that is 1 for male, and we get the male salary regression equation like that. And female salary is like that, female salary regression equation like that: beta I is equal to beta yi is equal to beta naught plus beta 3 x plus ut. And if we include the second dummy variable, a male and a white, then regression equation for the male salary become as beta naught plus beta 1 plus beta 2. Here we have 1 and here we have 1, so we get the salary of male white regression line become as. And for the white female salary regression equation become as yi is equal to beta naught plus beta 2 plus beta 3 x plus ut. So with the help of 2 dummy variable, we have find the 2 different qualities of our male or female salary related information. Okay, let's discuss the structure break, or how can we find the structure break with the help of dummy variable. Let's see the case study, like that is case study of Pakistan, and we have information of Pakistan from 1947 to 2008. Any type of information like consumption, like GDP, like population, like these type of information has been given to us, and we are taking the data from 1947 to 2008, and we have a number of observation 62. And you know that the Pakistan faced a structural break in 1971, when one part of Pakistan has got independence and become a Bangladesh. So we have to introduce a break at 1971, and now we have a two part of the data from 1974 to 1971, 47 to 1971, and we have a number of observation 25, and we have a data from 1971 to 2001, and we have a number of observation 37. Now we use the chow test for testing the structure break in our data, and then we use the dummy variable for finding structure break in our data. The show test is that we have a two regression line here, like here when we have a number of observations 25, we have a regression equation yt is equal to lambda 1 plus lambda 2 xt plus u1t, and we have another regression equation like n is equal to 35, yt is equal to rho 1 plus rho 2 x t plus we can put here sorry for that, here we have a error term 2 u2t, here we have a u2t. Now we conduct the show test. The first step for the show test is regress yt on xt for the period of 1947 to 71 and regress yt on xt for the period of 1971 to 2008. Step 3, and then find the residual sum of square for the period of 1947 to 71, and the formula for the residual sum of square is that summation yt minus y hat square, or you can use RSS, and here we are we have divide our total time period into two parts, so that's why here we are getting the residual sum of square, first residual sum of square, and you can use another formula for the residual sum of square, summation yt plus summation lambda y plus summation lambda 2xy here, and find another residual sum of square from this estimated regression line from which we have a data from 1971 to 2008. So here we have residual sum of square, second residual sum of square, and the formula for the second residual sum of square is given here. This is step 1. Step 2. Sorry, this is known as, these two residual sum of square are known as restricted residual sum of square, RSS1 and RSS2. Step 3, sorry, step 1 and step 2 and step 3. Step 3, regress yt on xt, and you have to use the full range data from 1947 to 2008, and from this data you also find residual sum of square, and this is this residual sum of square is unrestricted because here we have not put any type of restriction, so technically this is called unrestricted residual sum of square. So normally some books write it URSS, and some books call it RSSS 1, 2, 3, so on. So this is our unrestricted residual sum of square. And step 4, so keep in mind that the residual sum of square of first and second, if we sum the residual sum of square first and second, they must be equal to the unrestricted or total residual sum of square. If not, then there may be the structure break or like that type of which we make a conclusion at the end of the chow test. Okay, apply F test. So keep in mind, from here you can apply F test, and all these steps of the F test can be put here, and you have to conduct all the steps which are involved in F testing procedure. You have to put it here. Okay, now you find the F calculated value. From these steps you get F tabulated value, and from this you get the F calculated value, and the formula for the F calculated is F is equal to RSS your unrestricted residual sum of square minus first residual sum of square plus second residual sum of square divided by first residual sum of square plus second residual and multiply by t minus 2 k is equal over k. Here we have RSS residual sum of square for the whole sample, RSS1 residual sum of square of subsample 1 and residual sum of square subsample 2, and t number of total observation, and 2k number of regressors in the unrestricted regression line, and k number of regressors in each unrestricted regression line. So you have to compare this calculated with your tabulated, and you know that if the calculated is greater than and tabulated, then you can conclude that there is a structural break in your data, and if not, then there is no structural break in your data. So if we see the example of Pakistan here, the consumption pattern or growth pattern, then if the calculated is greater than the tabulated, then we can say that there is a structural break, because half part of population as well as half growth indicators of Pakistan are divided into subgroup, that is one for the Bangladesh and the second for the West Pakistan, which is now known as a whole Pakistan. Dummy variable. Now we use the dummy variable for finding the structural break here. Okay, we have yt is equal to beta naught plus beta 1 d1 plus beta 2 d2 xt plus beta 3 xt. Now we are using the first dummy variable 1 for 1972 to 2008, and now regress the equation. If beta 1 and beta 2 are statistically significant, then there is a structural break in the data. You have to run the regression line and yt on x, and you have to use the data from 1971 to 1947 to 1971. You have a regression line here, yt is equal to beta naught plus beta 3 xt, because here we have suppose that at here for the period of 1972 we are supposing 1 and otherwise 0. So here we have a 0 and here we have a 0, and we get the regression line for the period of 1947 to 1971. Okay, we have another regression line, that is yt on xt, and we are using the time period 1971 to 2008, and here we have a regression line yt is equal to beta naught plus beta 1. So see here, if we put 1 here, we get two constant, beta naught and beta 1, and here we put two constant. But here if we put a 1 here, then we get a two slope, beta 2 and beta 3. So here we get a beta 2 plus beta 3. There are two slopes and two constant at the same time. If beta 2 is insignificant and beta 1 is significant, then our regression equation become yt is equal to beta naught plus beta 3 xt plus ut. So if our beta 2 is insignificant, beta 2 is insignificant but beta 1 is significant. So we and beta 1 is significant. If we have a another equation, yt is equal to beta naught plus beta 2 plus beta 3 plus ut. If both beta 1 and beta 2 are insignificant, then our regression equation become as yt is equal to beta naught plus beta 3 xt plus ut. So in the case of both our dummy variables slopes are insignificant, we get this. So here we see the graphical representation of the four cases. If we have both beta 1 and beta 2 significant, then our regression line become as, and if we have beta 1 only insignificant, here we have a beta 1 insignificant, then our regression equation become as. Here the constant of the both regression, here we have a both regression constant are different and slopes is also different, but here we have a slopes are different for the both subsamples, but the constant is same if we have a beta 1 insignificant. But if we have a beta 2 insignificant, then our regression line become as, with two different constant. In the long run, both regression line will be merged. Maybe here they will become same, or they are converging to one another. And if both are insignificant, if both beta 1 and beta 2 are insignificant, then our regression line is only one, because here we have a yt is equal to beta naught plus beta 3 xt plus ut. So see here, if beta 1 and beta 2 are insignificant, then it means this part is 0 and this part is 0 and this part is 0. So we get only beta naught plus beta 3 xt plus ut. Okay, piecewise linear regression. when we have a dummy variable and we want to find we want to run the piecewise linear regression, that we have a yt is equal to beta naught plus beta 1 x1 plus beta 2 x1 plus x static. This is the interaction term which we are going to find here. D is dummy variable plus ut. So here we have a dummy variable, one for sale is greater than x. So if sale, we want to check the impact of sale on commission. As we know that if the sales are increasing, then the salesman get a commission, or the representative employees are getting a higher commission. So that's here we have a one for if sale is greater than x and 0 otherwise. So let our beta 1 is equal to 0.5 and beta 2 is these are the supposed value here. Here we are just supposing these value for the interpretation point of view. So beta 1 is equal to 0.5 and beta 2 is equal to 0.10. So if beta 2 is significant, then up to x says beta 1 is 0.5, which means that 25% commissions can be earned by the employees. And if we have x beta 1 plus beta 2 is on above, we are getting the above on the sale from x2, x, then we get beta 1 plus beta 2 and we are getting 0.35. This means that employees are getting 35% commission. So if beta 2 is insignificant, then we have a yt is equal to beta naught plus beta 1 x1 plus ut. So let's see the graphical presentation of, here we have a dependent variable commission and independent variable sale, and from the starting point our constant will be same, and after that point if beta 2 is significant, then commission will be increased, and if beta 1 is significant, then the commission will remain a constant, somehow remain a constant. So this is known a piecewise linear regression analysis. Dummy variable for semi-log model. Okay, let we have a salary function, that y is salary as a dependent variable, and here we are using a male or female salary as an independent variable. Male or female are qualitative variable, and we are using these two as an explanatory variable. And we have ln yt is equal to beta naught plus beta 1 d plus ut. And here we have a dummy variable like 1 for female and 0 otherwise. Keep in mind 1 for male, female and 0 otherwise, and beta 1. So keep in mind that beta 1 is significant, then the salary of female is equal to the constant 0 beta naught plus beta 1. So see here, if we put a 1 here, then we get, because here we are supposing that a 1 for female, then our female salary equation become as ln yt is equal to beta naught plus beta 1. If beta 1 is insignificant, so sorry for the in place here, insignificant is written. If beta 1 is insignificant, then the salary of a female is equal to the male salary. Like we have here 0, then it means that the beta naught is representing the male salary. Then if our beta 1 is insignificant, then the male and female salary become equal to each other. Okay, note that don't take the log of a dummy variable. So keep in mind that we cannot take log of a dummy variable. This is a main rule for the logarithm, because in dummy variable we have 0 and 1 value, and we cannot take the log of 0 value. So we have now till now we have discussed the definition of the dummy variable, the uses of the dummy variable, and how can we find this dummy variable trap, and how can we avoid this trap, and how can we find the structure break in our data or in our model with the help of dummy variable, and how can we find the piecewise linear regression with the help of dummy variable, and the log and semi-log model in dummy variable. Okay, this is all about. See you with another video. Ciao.